So now let us do some immediate applications. So first is that if HNX is 0, if there are no n cells, then HNX is 0. Yeah, that is obvious because it is precisely what a CW complex would. If we are to compute directly, that will also give us 0. But this method also gives us 0 if there are no n cells, because xn comma xn minus 1 will give you 0. Yeah. So if there are no n cells, then this will give you 0. Not no 0 cells, but no n cells. Yeah. Second is if X is a CW complex. So the first line you should know that X CW complex with no n cells. 0 is incorrect there. Yeah. On the other hand, if X is a CW complex with k n cells, then HNX is generated by at most k elements. So how do we see this? So first of all, you should go back to previous slide and look at the horizontal sequence. Yeah, there's only one horizontal sequence, and look at that. So yeah, if it has k n cells, then HNX is generated at most by k elements. So let us elaborate this on a bit further. Now it is obvious that HN comma xn minus 1 is generated at most by k elements. Yeah, because obviously there are k n cells, so only these k cells can be the generator of xn comma xn minus 1. Yeah. Now you know that Dn acts on this group. Yeah, so this part is clear. It's generated by k elements precisely because there are at most k cells, k n cells. Yeah. Now kernel of Dn, actually there should be implication sign now. Kernel of Dn is generated by k elements because Dn in the horizontal sequence, Dn acts on xn comma xn minus 1. Now if kernel of Dn is generated by k elements, then obviously HNX, which is kernel of Dn over image of Dn plus 1, will be generated by at most k elements. So third is very simple. It simply says that you do not have anything. If you have something in one dimension and 0 in the other dimension, the cell complex becomes really easy. Yeah, this will be more clear in an example of CPN. Actually, we are writing this point precisely so that we can just compute CPN. So if there are no two of its cells are in adjacent dimension, then HNX is free abelian with basis the corresponding n cells in X. Yeah. So you need to keep into your mind. First of all, look this up in Hatcher. On page 140, look this up in Hatcher. And the example you need to keep in mind is of CPN. Now in CPN, you know that the structure is such: you have one 0 cell, then one 2 cell, then one 4 cell, one 6 cell, one 8 cell. So you have these cells not in adjacent dimensions, like no two of its cells are adjacent because they're only in even dimensions, so the odd ones are not even present in CPN. So those are 0. So obviously Hn, that means is generated by that particular n cell in the nth dimension. Yeah. So CPN, I will write it now. Yeah, so this is what CPN looks like. So now let us draw the chain complex. So part 3 says you do not even have to draw the chain complex. You just say that homology group H0 is integers, H2 is integers, H4 is integers, H2n is integers. Yeah, and everything else is 0. That is what part 3 says. Yeah, HNX is free abelian with basis 1-to-1 correspondence with the n cells. So H0 is integers, H2 is integers, H4 is integers, and so on. Yeah, but I'm writing the cell complex so as to make it clear. So this is 0, C2, C1. Okay, so this is C0. So now obviously, since this is 0 map in between, in even dimensions we have the cells and the odd dimensions we have nothing. So now you can directly compute the homology or use part 3. This is C2n, yeah. So HI would be what? It would be, obviously now use part 3, say it is directly generated by the basis element, so it is Z for I equals to even, yeah. So for an even number it is this, and it is 0 otherwise. That is pretty much it.